So some of you might have already heard this joke, so I'm sorry about that. But why did the smart contract go to therapy? Because it was feeling insecure. So obviously, there's unfortunately other parallels as well. Just like therapy, trying to make smart contracts secure is very expensive. So I'm trying to sort of make this easier by providing both a framework in which to verify smart contracts and a set of properties that we think generalize really well, because we've not been able to actually find a consensus of like, oh, these are some properties that you really want to prove for all smart contracts, and these are desirable. So we tried to come up with a couple ourselves. And these are Validity, Liquidity, and Fidelity. I've stolen the icon from Fidelity Investments because I couldn't find something better. So hopefully that's not a problem, but just as a disclaimer. I'm going to go into more detail later, but the idea of these properties, explained simply, is so validity is that the contract, if it's in a valid state, any transition leads to another valid state. Liquidity is saying that from any state, you can extract the value out of the contract. And fidelity is saying that the internal representation of value in a contract is always the same as the actual value locked by that contract. And like I said, I'm going to go into more detail about these later. Now, these properties, some of them might sound really simple, but they're actually, even so, they're really important. So for example, right, if we had a proof of liquidity, then that would have prevented the parity bug from the parity wallet, which resulted in $150 million worth of Ether being deadlocked. And so basically never able to be removed from the account, from the wallet. And similarly, Fidelity would have prevented the DAO bug, which resulted in 60 million worth of Ether being stolen. In order to do this, we also needed some examples. So I have three sort of working simple smart contract examples: an account simulation, a multi-signature wallet, and a distributed exchange. I'll go into a bit more detail as to why these were chosen, but just to sort of cover a sort of wider variety. And the idea that we've been doing is we've been trying to prove these properties for the smart contracts in Agda, and then use Agda 2HS to export the contract as Haskell, basically, which you can use almost directly in Plinth and compile it to the Cardano blockchain. The sort of pipeline looks like this. So we have the properties on the left. Obviously, you can add whatever other properties you want there. And then you prove these properties for a model, which we model as a state transition system. Now, if any of you have had any experience with like proving things, right? Cardano validators are functions that return a Boolean. So if you try to prove properties of functions that return a Boolean, that's just really awful and nasty. So instead of that, we use a state transition system, which is much easier to prove properties about. And this also sort of ties in with the old state machine formalism that sort of was supposed to be mainstream back when I started research, but didn't end up like working out quite as we had hoped. After you prove these properties about a model, then you have to prove a sort of equivalence between the model and the validator. And again, I'm going to go into detail about this. And all of this sort of left side section is done in Agda. Then, like I said, you use Agda 2HS to get a Plinth validator, and then you can compile and run that on Cardano. So I'm not going to spend too much time on this slide because I'm sure everyone knows, right? Cardano is UTXO multi-asset based. But the unfortunate reality is the most popular blockchain, Ethereum, and many others are account-based. So because of this, one of the main examples that we chose was the account simulation example, because we thought it would be really nice to also show that, hey, you can have accounts on UTXO. Now, this is a very naive implementation, so you wouldn't really want to do exactly this, because you just have basically, you have one major control state that has in its datum a map that tells you, denotes users as their public key hash and says what value they have in their account. Obviously, this is terrible because you just have a giant list in your datum, so it doesn't really scale. And we've talked about ways to make this like actually usable by separating this across multiple UTXOs or using like a Merkle tree or something. But that's not important for my presentation. So you only have one big control state, and obviously you have to start the contract at some point, put it on the blockchain. You can open an account for a certain public key hash, deposit some value into your account, withdraw some value from your account, transfer from one public key hash account to another public key hash account of value, and close your account if it's empty. And obviously, well, not obviously, but we also have a stop sort of function that allows us to clean up the contract if you don't want it to be on the UTXO anymore, so it doesn't have to just stay there forever. And obviously, this also helps with actually getting the money out of the account, out of the UTXO. But more details on that later. Like I said, we use the state transition system, and it looks something like this, right? You have some optional parameters, and then you start in a state, you transition with an input to a different state. And we try to sort of model the stateful progression of the contract using this. We also have, obviously, the sort of reflexive transitive closure, not quite, of this state transition system, basically saying that we can stay in the same state, or we can go through a sequence sort of inputs by doing the first one and then doing the rest of them. It's fairly self-explanatory. You apply it inductively, but it helps for our proofs. So in Agda, this looks like this. Like I sort of mentioned, the parameters are optional. So in this case, I've omitted them because for the example that we're using, the account simulation, there aren't any parameters that we care about. But for example, for the multi-signature wallet, you might care about how many signatures are required to issue a payment, or which ones the authorized signatures are. And for a distributed, the DEX, the distributed exchange, you might care, in the way that I've written it, the specific version, you might care what token you're exchanging for what token. And that's what would count as parameters. And this would be great, and it was the primary thing that I was doing, and it works fine just for smart contracts, but, right, Cardano also has minting policies, which are important for a lot of different reasons, and they're really quite similar to validators, right? So validators look something like this. You have the optional parameters, datum, input, script context, and then you produce a Boolean at the end. Token minting policies also have, so these are both parameters, but I've taken both of them out because they're the ones that are necessary for a thread token, which is the main application that I'm using minting policies for. And then again, an input, they don't have a datum, they also have the script context, and they give a Boolean out saying if you can mint or burn however many tokens the fields in the script context tell you. And it would be really nice to be able to use, and it would be really nice, and you can use the sort of same method to prove properties about the tokens at the same time as you're proving properties about the validator. In particular, right, I mentioned, and some of you might be aware about the thread token idea. One of the problems with UTXO, right, is that when you put the smart contract on the blockchain, right, the first time, you can put whatever you want on it, which is not great, right? The validator itself, whatever it has in it, has absolutely no control about its initial state, which is kind of bad because a lot of the properties that we a lot of the properties that we have say that if you're in a good state, you stay in a good state, but you also need to start in a good state. And for that, we use the minting policy. So we mint a token when we put the smart contract on the blockchain, and that minting gives us the initiality sort of the smart contract. This is mentioned in a bunch of the original sort of UTXO MA papers and stuff. So I've kind of been using the idea. And obviously, right, once the contract is on the blockchain, you can just ad nauseum sort of repeat the running transactions that sort of keep the smart contract continuing on the blockchain. And eventually, right, you might have that sort of stop transaction that removes the contract from the blockchain, and it should also hopefully burn the thread token alongside it. So this basically means that we have to adjust our state transition system to account for this, because we can't just use the one state transition. We need to have a special one for minting the token and a special one for when you're both minting a token and running the validator, for the equivalence at the end, right? Because this is now a complex system of two different functions, not just the validator anymore. And you need to be able to separate between them. So we've kind of gone from therapy to couples counseling, which I'm not sure if it's better or not, but here I am. Right. Now let's look, I think, at the, right, so let's look, so the evil wall of text has appeared. I'm going to try to not spend too much time on this, but so this is an example transition in the state transition system. So if we start at the bottom, right, we're in a state, we're trying to withdraw from a certain public key hash account a certain value and end up in a new state. There's probably 100 questions that we could go into here, but right, so you want the datum to be of a pair of a token, and this is the thread token asset class that the smart contract needs to know. And this has to be in the datum, because so you would think, oh, that's something you would put as a parameter, but you can't put it as a parameter because then they would cause cyclical definitions between the token and the validator script. So you put it in the datum, and then you actually have the account map here. And then there's a bunch of sort of bookkeeping, right? You want the public key hash that you're trying to access to be a signer of this state. You want to look up in the map and find a value, because you might not find an account at all. You want that value that you're trying to withdraw to be positive. You want the value that you have to be greater than the value you're withdrawing. And then you want the new datum, right, of the continuing smart contract to have the same token asset class. This should never change. And then you're inserting the new value, right? You've withdrawn some value from that public key hash in the map. And you're also updating the value. Now, I've chosen to write this, sort of spin it around so that it has pluses instead of using a minus, because it's easier to prove stuff for plus than for minus. But, I mean, this is commutativity, right? Like, you can figure it out. And then at the end, there's a bunch of sort of annoying bookkeeping where, like I said, so the state, the abstract state in our model needs to somehow understand when the smart contract exists on the blockchain and when it doesn't. So that's what continues does. It says, right, if I'm using the name continues because the function in Plinth that sort of does this is get continuing output. So it basically tries to find if the smart contract exists on the blockchain, then this is true. And then has token also says if the token is actually contained in the value locked by the script. So obviously, right, for a runtime transition, you would want it to exist and to keep existing, and to have the token and to keep having the token. And obviously, if when you're minting it, you don't care about, well, you only have one state. And then when you're burning it, you would want the has token of S prime and continues of S prime to be false. Anyway, so this is a sort of example of what the rules look like. So, right, I mentioned the properties. Let's go a bit into more detail. So validity, right, I should have set a timer so I knew how much time I had, whatever. We want to say that when you transition from a valid state, you end up in another valid state, and also the initial validity, right, that you start in a valid state. Now, what validity means, like validity itself is, right, a predicate that varies from contract to contract. So in our example of the account simulation, this is what I've come up with. So your state is valid if it's stopped, right? So if the smart contract doesn't exist, that's valid, right? So if there's no continuing contract, that's a valid state you can be in. But if otherwise, you want, right? So remember the type of datum is a token and a list, and then you go through that list. You don't care about the public key hash, but you care about the value. You want all the values to be positive, because it doesn't make any sense for somebody to have a negative amount in their account. So this sort of acts as an invariant on the state, and it's a little bit hard to say that you've got it right. But what validity sort of ends up doing is it's necessary for the other proofs down the line. So when you're missing something down the line, you realize, oh, that was supposed to be part of what a valid state means. And then, I mean, the proofs themselves are not particularly interesting, right? You're just saying, well, you have that the initial state transition where you just create the state, and you want that state to be valid for any state and any parameters. And then you want the sort of, for any two states, if the first state is valid, and you can use a series of inputs to multi-step to a new state, then that state is also valid. So that sort of gives us the property we want. Then liquidity, right? So here I'm going to say, assuming honest participants in infinite time, because I'm making a lot of abstractions, right? I'm proving stuff in Agda, and I'm kind of abstracting the ledger, and I'm going to go into more details about that later. But right, you're in an account simulation, right? Nobody else is allowed to withdraw money from your account. So you're just sort of assuming that this contract is liquid if people actually want it to be liquid, because if somebody puts 10 ADA into their account and then never takes it out, then you're never going to be able to do that for them. So I'm just sort of assuming that people actually want to do it. Like there is a path, not necessarily the path that will be taken, but that it exists and that it's sort of readily accessible.
Your assumption of infinite time worries me a little.
Well, I guess I put it in there because I'm just not representing time at all. So,
I would prefer to see some notion of finite time.
So that, I guess it's a reasonable extension that could probably be done. I've just not done it yet. I'm mostly concerned with the sort of internal logic and less about. So I'll go into more detail about that later. So it looks something like this, and there's a bunch of questions that can maybe rise up here. So if you, for any state, as long as that state is valid and it exists and has the token in it, then there will exist some other state and the series of inputs such that we can get to that state and the value is 0. Now, I'm going to tackle some of the more important questions here. Obviously, a smart contract can never have 0 value in it because there's a minimum amount. So this is the sort of liquid value in the smart contract that's sort of like modulo what you would expect. So when you put the smart contract on the blockchain, you put some amount in it, and I'm normalizing that as being 0. And then I'm saying, okay, well, the actual liquid amount that we care about is what people actually put in. And then now you're saying, well, okay, so you've put these constraints that the state has to exist and has to have the token. So why not put those in the valid sort of invariant? You could, but that doesn't actually help you. Because then, right, this basically allows us to more easily discharge the state in which the smart contract is stopped. Because if the smart contract is stopped, then it doesn't exist. And technically it doesn't, because it doesn't exist, it sort of intuitively doesn't have value in it. But you can't enforce that, and then it sort of messes up the equivalence between the validator and the state transition system. So this is a strong enough property, and it also keeps sort of validity less complicated. But anyway, we can, if somebody has more questions, we can maybe discuss them later. Right, finally, there's Fidelity, which states that the internal representation of value in the smart contract datum is always equivalent to the true UTXO value. So this is a property that Phil and I came up with from reading some papers by Herlihy and one by Sofia de Strofolo, which basically claimed, right, so people were over-focusing on, in the DAO exploit, they were over-focusing on the fact that, reentrancy was the problem, but they said, no, actually, reentrancy wasn't the problem. The sort of deeper underlying issue is that the contract thought you had an amount in it that wasn't true. And that was caused because of like the reentrancy and not atomic operations. But if you could prove that no matter what you do, the internal representation is consistent with the true value, then you wouldn't have that problem. And that's kind of neat, if you can have that. And this is, again, sort of an invariant of the state. You also need the initial version, but I didn't put that in the slide because it's sort of trivial. And again, sort of what the sum value of getting the internal representation will vary from contract to contract, but the sort of fidelity property will always look the same, right? The actual value of the state has to be the sum value of the internal representation, and then if you transition from that state to another state, then you have the same sort of property.
So what do you mean by value here? In the Cardano context, you're meaning ADA.
I mean, I'm actually.
Tokens. You can create tokens or destroy tokens. You can burn tokens, right?
Yeah. So.
You can burn tokens, but I don't. In terms of value, my understanding is that would include the native tokens, not.
Right. So you then fidelity. You've got a very strict notion of fidelity, right? That you can't mint or burn any native tokens.
Well.
Isn't this the value locked by the contract?
Yeah, it's the value locked by the contract. So like it's how do I so you can if the contract expects you, like because you have a specification of the contract, right? And this is a proof about the specification, the model and the specification. So if you're expected, let's say you contain 10 ADA and 5 dog coins, right? If you have an operation called woof that burns 1 dog coin, right? Then the specification this sum value, the specification will know, well, it's supposed to know, right, that you're burning a token, you have less of it. So it doesn't, what the specification cares is that the token is gone. It doesn't care if you've burned it or given it to somebody else, I guess. So you can burn the token. And for the account simulation, I'm using integer to represent value, but for the DEX, I'm actually using a map of account to value, because that one has to care about tokens. So I guess I am using, for at least one of them, I'm using a more complex data structure for value that does use tokens. So it should be able to handle minting and burning if that was something that we cared about, in theory.
It's not saying that S dot value before equals S prime dot value.
Yeah.
So you can make the very things.
Yeah. Yeah. Well, so I'll talk a bit about this. But so for some smart contracts, you don't have an internal representation of value. So this property is trivially true, but I'll mention that a bit later. Right, so okay, so we've proven this property is about a model. What does that have to do with a smart contract, right? I also write the smart contract in Agda, and then I try to prove an equivalence, right? Sort of equivalence. This is not an equivalence in the same state, which is why I use a squiggly equals. But basically, I'm saying, okay, well, there's an argument. So in Agda, for those of you who don't know, set means type. So there is an argument, and if you have a function that returns a Boolean and a sort of unary relation that is inhabited for the same sort of that same argument, right? If the function returns true, so that the Boolean accepts the sort of transaction, then there is a state transition equivalent to it. And equally vice versa, if there is a state transition system, then that corresponds to the validator returning true. So I try to prove this. I prove this equivalence basically for a validator that I've written in Agda. So just quickly coming back to here, right? So the validators take some parameters, a datum, an input, script context, and return a Boolean. And the Agda policy has, so this, because this is a thread token, excuse me, it needs to know the address of the smart contract that it's bound to, which is why this is a parameter, and it needs to be an NFT, which is why it has the TX out reference. Philip mentioned it this morning. So these are sort of necessary parameters, and then this input is actually usually just sort of the unit type, because you don't really care, but it is here as a type, and then again the script context. So what is going to be our argument, this A, right? It's just going to be all of these things together, right? The parameters, the address, the TX out, the label, and the input. We only have one input because we don't actually really care about the input of the token minting policy. And then, right, we need to classify what state that represents, right? We have a phase that says if it's initial, running, or terminal, right? These correspond to these ones that we mentioned before, because in the initial one we're minting, in the running one we're validating, and in the terminal one we're both minting and validating. And we have, yes?
I was just surprised in the terminal one you've got two states. I thought it would be a bit, you would just have one, you say something is the last.
I guess you could do it without, but so actually, well, you'd need, I guess you could do it, but then you'd have some information that's sort of like weird. So basically, right, when you try to get the contract to stop existing, right, it goes into a state in which it doesn't exist anymore. But so the model needs to be able to represent this kind of, because you.
Oh, it's a final step, but you don't mention the initials. But the initial S is the initial one.
Yeah, I guess. You could have this one. You could have it sort of fully circular, where this one has an S and an S prime, and you could go from a sort of end state back into a restarting state. But I feel like this was simpler, I guess, so I just like sort of kept it.
So the terminal state allows for finalization. Is that the idea of finalization of resources, for example? So you're in network systems or distributed systems or concurrent systems, you often have to finalize the resource usage when you're going into the final state. So the final state is
sort of, yes. Sort of.
Sort of. Yeah.
Yes. So, I mean, okay. Basically, the equivalence looks a little bit ugly, but basically it says what I've been saying previously, right? So you have this argument, and you use the classifier to know what phase you're in, and then if you're in the initial phase, then you have the policy, right? The minting policy, and this TT is just the unit type in Agda. Like I said, this is the input, and we don't care about it. And these are the parameters and the context. If you're in the sort of running phase, you just have the validator, right? And if you're in the terminal phase, you're both validating to spend the contract and burn the token. And then this has the sort of equivalent states in the state transition system, right? You can just, these are just sort of getter functions that like extract that information from the argument. So, like I said, I'm using a sort of abstract definition, not like actually the ledger. So basically, the stuff that the state expects to have in it, you can extract out of the script context and so on and so forth. And obviously the data and the inputs in the script context and so on and so forth. And well, yes, you have the initial state where you're minting, just starting, and then you have the continuing sort of ones that you can repeat, and then the terminal one where you sort of finish and burn the token. And you prove that these functions are equivalent with this sort of, this equivalence definition. And that gives us a sort of transportation of the properties from the model to the validator, and then the validator we export with Agda to HS, which doesn't have a fully verified pipeline, I guess, but it's better than nothing. And then we can run that on Cardano. Right, so I've done it for, like I've said, I've done this for multiple smart contracts, but like there's not necessarily that much to look into it and as part of this presentation. This is the multi-signature wallet as presented in the sort of UTXO paper by Chakravarti et al. That I've sort of used as a blueprint. I've had to amend it a bit, right? So it has a start and the close transition as well, and I'll talk a little bit more about this in a bit. And then the distributed exchange is very simple. The idea is that you put many instances of this smart contract on the blockchain, and each of them is saying, I'm exchanging currency A for currency B at a certain rate, right? This rate. And then you can update the rate or the amount, and somebody can exchange some amount of that currency at the current rate. And obviously, the owner can close the exchange whenever they want and recover their funds. So we found some interesting stuff. MinAda causes some issues with liquidity, especially for the multi-signature wallet. I found a very interesting bug where you can actually deadlock as it's written in the original paper, you can cause a deadlock because you don't have a way to just close the smart contract. And if you perform payments in such a way that you end up, min ADA is a sort of variable, but let's assume it's 2 ADA because it was for a while. If you end up in a state where the multi-signature wallet has exactly 3 ADA in it, or lower than 4 basically, you can never propose a payment because either you'd have to propose a payment of lower than 2, which can't be made, or you'd have to propose a payment greater than 2 and be left with less than 2, which you can't. So that would cause the contract to get deadlocked forever, which was undesirable. Right, I mentioned it previously, right? So fidelity is trivial if there's no internal value, and that kind of sounds bad at first glance, right? I've just said that these are nice general properties that you want for multiple different types of smart contract, but actually this is great because if fidelity is trivially true, then you get all of the properties that you want, and it sort of means that you're immune to those types of attacks by design, and you also have to do less work for it. So in a sense, it's actually fantastic. Finally, more contract-specific properties are usually easy to prove. They're kind of sort of true. Most of them end up being like true by design. For example, right, you might want to check stuff that like for a certain public key hash, you can always get all of their money out of the account. And that's usually very simple. You can just give it the example of I withdraw money from my account and I get all of it out. But yes. Right, to sort of just do a quick recap, right, we have these 3 properties, Validity, Liquidity, and Fidelity. We've proven them for 3 example smart contracts, and we're going through from Agda to Plinth and then compiling to Cardano. So hopefully, after all of this work, the smart contracts can feel sort of unchained from their insecurities, at least slightly. But there is one more thing that I've done recently. So, like I mentioned, right, I'm currently abstracting away the ledger details, and I'm using the sort of abstract notion of script context where I'm saying, right, the script context is a very complicated data structure, and you need to do a lot of stuff to actually get things out of it. I'm just sort of saying, for the purposes of my my validator, that okay, well, the script context has in it your continuing value and your continuing datum, and you don't have to go through a list of outputs, find the one locked by the thing that has your address in the script purpose, and anyway. Which does also mean that, unfortunately, I don't do the things that James was very excited about, which is sort of prove properties about the functions that process the script context or whatever to actually get the datum, get the value, and so on and so forth. I'm just sort of assuming that those work. But it is possible to do those. So, right, the formal ledger specification exists. I'm sure all of you have heard about it. So that's a much better place to do those types of proofs because they actually have a proper sort of script context representation. You can say, okay, here's a function that gets me the datum, and here's a proof that it gets me the datum and doesn't give me a faulty datum that's too big, or et cetera, et cetera. So can we replace our abstraction with the existing ledger model? Not quite as easily, unfortunately, if you want to keep the Agda to HS sort of pipeline to be able to compile it to Plinth. You can't do it because the ledger model depends on the standard library, and Agda to HS is incompatible with the standard library. There's also some other side issues, which are the fact that the ledger model is still sort of under development, and it has a lot of useful stuff in it. But for example, most recently I've done some other work, sort of transposing these examples that I have the 3 smart contracts into the ledger model and being able to run some sort of traces on the computational UTXO rules on them. And the token algebra that they have has some issues with it. So everything is fine if you just have ADA. But if you try to put any amount of tokens in, the computation hangs endlessly and eats all your memory and then crashes. So I've not figured it out myself. I've told it to them, and they've not figured it out at face value. So hopefully there will be something done about it. But at the moment, you can't really get a one-to-one correspondence because I kind of need tokens for what I'm doing. But you can get something sort of partial, which I have done, right? So you can prove another equivalence even between the simplified version without tokens in it, by putting them both in the same file and saying, okay, well, you have this abstract validator. Label means datum here. I should have probably fixed that. Sorry. So the abstract validator is the one that we have, that I've been mentioning, and that I have in sort of an Agda2HS universe. And then we'll call that F. Then you have a real validator, which uses the complex data types on the formal ledger specification. And then, so this is kind of simpler to write an equivalence for, because they're both functions that return a Boolean. So you just want them to return the same Boolean for the same inputs. But obviously, there's different types for the inputs. So the equivalence looks something like this, where you have some ways to lift the non-abstract versions to their abstract versions for the label, the input, and the context. And you might notice that the context also depends on the input. Like I said, in the abstract script context, I've set, basically I'm saying, well, the things that you can get out of the script context are just there. And some of those things depend on the input. Like, for example, if you're making a payment, so for the withdraw example, right, you'd care about a payment in the script context to a certain address. And the address for that is the public key hash, which is in the input. So you need the inputs so that you can process the real script context into the abstract version. But anyway, and then you also only have it one way, because obviously, so, but this is fine because it's kind of the important way. So if you have the real sort of the formal ledger specification version of the label, the input, and the script context, you can lift them to the abstract version, and you're saying, well, our abstract validator returns the same value as the real validator, and you kind of, right, inherently, anything in there that isn't, like, that you're abstracting away can't affect the computation, right? Because otherwise this equivalence wouldn't hold. So you kind of mostly care about the actual implementation being the same. You kind of mostly care about the abstract implementation being in tune with the real implementation, not the real implementation being in tune with the abstract implementation. Because the abstract implementation, for example, will fail some things when it doesn't, because it has the token mechanism in it. So it will fail some things that the real implementation will accept. But you don't really care about that. And obviously, once you have once you have the token algebra, you'll be able to do it both ways. But until then, I guess this is the best thing I can do, and it provides a nice sort of link between my work not longer being in a void and actually being connected to the formal ledger spec. And yeah, I think that's everything I have for today. I've put up some stuff on the final slides so that we can look at it. But if you have any questions, I'd be happy to try and answer them to the best of my ability. Not sure if that was too fast or not.